Okay, let's get started. Are any of my GSIs here? Is there a GSI in the house? Hi, I need to ask you a large favor because I've once again forgotten to bring the clicker base. So I'm hoping that its first clicker is late enough in the lecture that you'll be able to take this key, go to my office, open it up, find the clicker, which is in sort of pinkish orange bubble wrap on a shelf somewhere. Okay, let me get your attention. Now the crucial word in the sentence, let me get your attention, is what? Your. Thank you. Very good. The crucial word is your attention. And because the word your, in this case, could be interpreted as first person, second person plural, you might think that I'm actually not talking to you and that I'm just talking to the group in general. Instead, you should assume that what I mean is your attention. Your attention. Your attention. This is a whole different class, behavioral linguistics. Thank you. All right, good. It's a different silly way to get your attention every day. So quick announcement, problem set 3 has been posted. Again, I apologize for the delay in posting that. I'm digging myself out of the hole caused by the sort of family health crisis that I faced a few weeks ago. The problem set is due 1 week from today. A tip, okay, there's 2 problems. They're both relatively long. Problem 1 is based on last week's lectures, and you should be able to do it based on what you currently know. For problem 2, just so you don't waste time, you should be able to do the first part based on today's lecture, I believe. But the second part will almost certainly require Thursday's lecture. If you want to take a stab at the second part of problem 2 after today's lecture, that's great. But if you start feeling like you're wasting time and spinning your wheels, then just hold off until after Thursday's lecture. Okay. So today, this is my week of getting caught up on everything. So I've fallen behind a little bit in the last 2 lectures. So we're going to be finishing up from last time. We've been looking at present bias preferences and the preference reversals and irrationality anomalies that arise. And I've done a little bit of work showing you how this beta-delta model of present bias preferences can explain some of those anomalies. And I want to finish that up and put a bow on it so that you are sort of as convinced as possible that the beta-delta model is a useful one before we start doing work with it. Then we're going to have to address a really interesting and challenging aspect of this model, which is people's beliefs about their future intertemporal preferences. Right? So one of the interesting features of a lot of intertemporal choices is that the decision you ultimately wind up making depends not only on what you do today, but also on what you do tomorrow and the next day and the next day, right? So if your preferred plan is to go to the gym Monday, Tuesday, Wednesday, Thursday, Friday, the implementation of that plan involves a choice that you have to make on Monday and a choice to make on Tuesday, one on Wednesday, one on Thursday, one on Friday. Which means, right, that when I'm sitting here on Monday trying to decide, like, what do I want to do, I have to be thinking about what my future selves will do, and that's going to depend a lot on what I believe their preferences are going to look like, right? Do I rationally believe, predict, expect that my preferences on Tuesday are basically going to be the same as my preferences on Monday, or do I somehow magically think that on Tuesday I'm suddenly become this guy with incredibly powerful willpower or no temptation or whatever? And that's going to turn out to matter a lot when it comes to intertemporal preferences. And so we'll be digging into, once again, this issue of rational versus irrational expectations. To accomplish all of this, I am going to have to kick butt a little bit on this first catching up bit. So I'm going to ask that you pay careful attention, and I'm probably going to take limited questions, if at all. If something totally doesn't make sense or if I make a mistake on the board, please let me know. But I'm hoping to just sort of bust through this. Okay. So we've seen some anomalies, right? Preference reversals, the $100 versus $105 thing, and a few others. And we came up with the idea that the underlying psychological explanation for these things is present bias, and then we made one tiny change to the Samuelson discounted utility model, the exponential discounting model, which was to turn it into a quasi-hyperbolic model where the discount factor is basically going to differ, right? The function is going to differ depending upon whether you're talking about now or sometime in the future. Okay, so the discount factor between now and any period t, this is a little bit odd the way this is written, but it's going to be regular exponential discounting if and only if you're talking about period 0. And then the discount factor of now versus any future period is going to be the exponential discount factor delta to the t additionally discounted by this beta. Now this is a little bit dorky because of course for t equals 0, delta to the t is just equal to 1, right? So basically what that's saying is I don't discount the present, and the way that I discount the future is this. I discount period 2 relative to period 1 by delta. I discount period 3 relative to period 2 by delta, 4 relative to 3 by delta, which is to say that I discount all future periods in this exponentially increasing way. But then I take all of that whole exponential discounting process, and I discount all of it by an additional beta relative to now, okay? Where both beta and delta are between 0 and 1. Okay, so what I do, in other words, I have this plan that unfolds from now, period 0, to the future. And what I do to compute big U of that plan, the utility of the whole plan, is I say, here's the undiscounted now payoff, U naught, okay, or U of X naught. And in both models, I don't discount that. But then what I do is I say, here's all the future stuff, which is that's the Samuelson sort of exponentially discounted sum of future utilities, and I'm going to take all of that and sort of just sink it down a little bit by multiplying it all by beta. And again, as I said last time, another way that you can represent that is to say, let's divide all of this by beta, so you would have 1 over beta times the present stuff, and then that beta would go away. So in other words, another way you can conceptualize this is that I'm going to do Samuelson exponential discounting on everything in the future, but then I'm just going to inflate immediate payoffs by 1 over beta, right, which is a number larger than 1. So you can think of either of those, and as I said, if you want to think about deflating the future, that's sort of capturing future time preference theory, and if you want to think about inflating the present, that might capture self-control theory, but mathematically, they're identical. Okay, mathematically, they're identical. That's the model. Okay? So let's use it first to explain the preference reversal anomaly that some of you exhibited in that very first iClicker question we did last Tuesday. So you had a situation where many of you chose 100 now over 105 in 2 weeks. And under the Samuelson model, that meant that the utility of 100 had to be greater than delta times the utility of 105. In the beta delta model, we have this additional variable that we stick in here. So what we say to explain this preference is that the utility of $100 now must be greater than beta times delta times the utility of 105 in 2 weeks, right? And what that implies is that beta delta must be less than the utility of 100 divided by the utility of 105. Okay? So it must be the case that you're discounting the 105 sufficiently to make it seem worth less than the 100 now. And that involves a little bit of this long-term impatience delta plus this additional bump of what we call short-term impatience, which is beta. Now, to explain the trade-off that you made between 100 in a year and 105 in a year in 2 weeks, right, we get sort of 100 in 52 weeks being unpreferred, if you want, to $105 in 54 weeks. So same time delay, but pushed out a year. What that implies in the beta delta model is that beta times delta to the 26, because remember, delta is the 2-week discount factor, must be less than beta delta to the 26 times the utility of $100 must be less than beta times delta to the 27 times the utility of 105. Okay, so again, what's happening here is you're doing exponential discounting on both of these things because they're both way out in the future, and one's a little bit further in the future than the other, so you discount it a little bit more, but you discount both of them by this big bump beta, okay, because they're both in the future, and frankly, I just couldn't give a darn. So what that means is now I can immediately, I can keep this inequality the same by just getting rid of the betas, and the point is that beta doesn't affect my choices between two future time periods because it affects both of them the same, so relatively speaking, it doesn't matter. Then, of course, I can do the same thing I did last time, which is to divide by delta to the 26, and what I wind up with is that to explain this choice, thank you very much, that was awesomely perfect, big hand for Waldo. And now the answer to where's Waldo is that he's in all of our hearts, and we love him. Okay, so now it must be the case that delta is greater than the ratio of the utility of 100 to the utility of 105. Okay? So the point is that to explain the choice between a delayed 100 and an even more delayed 105, all we need to know is what delta is. But to explain the choice between an immediate 100 and a delayed 105, we also have to know what beta is, what your present bias parameter is. So together, what these things say, right, is that beta delta must be less than this ratio of utility of 100 to a utility of 105, and that in turn must be less than delta. Well, this is no longer a problem, right? Previously, we only had delta to explain both of these things, so we had this anomaly, which is that delta had to be both greater than and less than some constant number. But now, the discount factor between now and one period in the future is augmented by this beta, which is less than 1, and that sort of explains what previously seemed like an anomaly. Yes? Good? That's the guts of the deal. All right. Now I want to actually confirm, test sort of view on whether or not that actually makes sense, which will give me an opportunity to plug in my base. Oops. Okay, so here's the question. Remember, we had this more complicated experiment, and what this experiment was, in stage 1, people were asked a question that involved an immediate reward versus a delayed reward, and then in stage 2, they were asked a very similar question that involved all delayed rewards. Okay, so in stage 1, they're asked, would you prefer $20 now or $50 in 1 week? And we had this sort of a hypothetical subject who would say, oh, I prefer $50 in 1 week. I'm willing to wait a week for an additional $30. Yes, I'm willing to wait a month for an additional $30, but no, I'm not willing to wait an additional 3 months for $30. So that was sort of our baseline hypothetical subject. And then we take that stage 1 choice, which is I'm not willing to wait 3 months for $30, and we ask them, how far into the future would I have to push those rewards in order for you to change your answer? Okay, so here's a situation where the person says, no, if you pushed it only 1 week out, I would still be willing to, sorry, do I have these backwards? No, sorry, that's right. If you push it out a week, I'm still going to be impatient and choose the early 20. If you push it out 2 weeks, I'm still going to choose the early 20. But if you push the 20 out a month, all of a sudden, I'm going to be willing to wait an additional 3 months. Okay, so we caught this person in a preference reversal, and we pinned down much more precisely the sort of the timing and sort of we quantified the preference reversal in some sense. Now, what we found last time, right? This is very similar to the thing we just did. Is in order to explain this under the DU model, the stage 1 choice required that. The stage 1 choice that this person makes required that delta be less than 20 over 50, which is equal to 0.4. And the stage 2 choice required under the DU model that delta be greater than 20 over 50, right? So exactly the same as what we just saw with the 100, 105. The question is, if we were to make a not entirely unreasonable assumption that delta is 0.9, right? In other words, a delta that under the beta delta model would explain the stage 2 choice, what would beta have to be in order to explain the stage 1 choice? Okay? Does the question make sense? Yes. In this case, the delta was the 3-month discount factor. But it actually, no, it's a 3-month discount factor. I think that does matter, and thanks for asking. So you guys do this in groups. Are there any other questions about the setup of the problem? Right? So you're just going to use exactly the math that I just gave you in the last slide and harness it to figure out what beta would have to be in order to get the stage 1 choice, given the fact that we've assumed that delta is 0.9. Okay, the room has gotten quiet. I don't know if that means you've all figured it out, or you've all given up, or you've all decided you can't stand one another. Is this making sense at all?
Yeah, I'm jumping on the chat.
So raise your hand if you are, say, within a minute of getting an answer. Raise your hand if you're done, got an answer. Raise your hand if you are not even, no, never mind. But the rest of you just sort of are like not feeling like you need more than a minute, is that right? Or raise your hand if you're at all willing to raise your hand for any purposes whatsoever. Okay, so that's what's going on. We have a low response rate. Take another 30 seconds or so. I'm going to open the clicker thing now. Okay, why don't I just give you another 5 seconds, and you can either make your best guess or enter no answer in 5, 4, 3, 2, 1, and click, 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 click. 2, 1, and let's stop. Okay. All right, so 70% said A, 29% said B. So I think what we're going to do is, just to save time, we'll let the 70% explain to the 19% and the, what is it, 19, 23, 29%? Those must be rounded off. Who said A that would be willing to explain?
Okay, what I did was I just set up 3 months with regard to delta thing, right? So I did U of 20 is greater than beta delta. I do a 50, and I just solved for beta.
Okay. And you got?
U of X equals X.
Yeah. So you got beta less than, am I getting this right? 20 divided by 0.9 times 50. And that equals 0.44. Yeah? So again, it's just the issue is we needed a delta greater than 0.4 to explain the stage 2 choice, where beta is not involved at all. And then the question is then, in the beta delta model, where the stage 1 choice is actually explained by beta delta, what did beta need to be to get the choice down to get the person basically impatient enough to choose the immediate reward? And the answer is that beta actually in this case has to be pretty dang low, which may or may not be right, but that's what this hypothetical example would say. So that's the math. Thank you very much, Andrew. Questions about that? Math makes sense? Does the setup make sense? What's important here is that you understand what beta is doing and why it's involved in the stage 1 choice and not involved in the stage 2 choice. All right. Now, if you've dug into this required reading from last week, the Frederick Lowenstein and O'Donoghue review paper, truly one of the best papers I've ever read in economics, but also just like takes a week and a half to read. These guys, they went and did the following. So this was all about preference reversal anomalies. And the other anomaly we've seen is that the implied per period discount factor necessary to explain people's intertemporal choices seems to vary, right? In the discounted utility model, it's always just delta. Every period is discounted relative to every other period by delta. And that shouldn't change depending upon what time delay you use to estimate it. And it turns out that it does. So we saw, for example, these results from Thaler back in 81. And I'm going to skip back and forth a little bit, where basically he said, I'm going to ask you to state indifference points between $250 now and some amount delayed by a month, some amount delayed by a year, some amount delayed by 10 years. And then I'm going to estimate from that what delta would have had to have been, what the 1 month delta would have had to have been in order to explain your choices under the DU model, right? So when you're making, so basically what he's doing is he's saying, I'm going to use your trade-offs now versus your trade-offs later to estimate delta in the way that we've been doing all along, in a DU model where there's no beta. And what I'm going to see is that depending upon how far out I offer you the delayed rewards, right? So there's always a present reward. You're trading off against a delayed reward. Depending upon how far out I push the delayed reward, the estimated value of delta to explain your choices gets bigger the further out I push the delay. Here's some additional evidence in support of that from this review paper that's on the syllabus, where basically what they did was they reviewed all published estimates of delta that used the discounted utility model, the exponential discounting model, to estimate delta. And what they have is they have the imputed per period discount factor, that's to say delta, on the vertical axis, and on the horizontal axis, the time horizon of the delayed reward. Okay, each study was based on some different delay. So these are all the different types of trade-offs people were asked to make. I have no comments on, pain, heroin, and corn. There's a short story in that. And basically, here's what you see, right? Going forward to this stuff, we have basically a 1 month, a 1 year, and a 10 year. So those estimates would be sort of right in here, right about there, and out here, okay? And so what they find in the literature is the same thing that Thaler found in his hypothetical experiment, which is that the shorter the delay to the delayed reward, the bigger of a delta you need to explain people's intertemporal choices if you're only using the exponential discounting model, okay? And that when choices are way out and when the delayed reward is way out in the future, a much larger, less sort of impatient estimate of delta will explain the results better, okay? Now what they did was so this is just a PDF cut and pasted into my slides from the paper, and they ran this regression line through. Now obviously these things, this is not a linear shape; it should be curved. They ran a regression line, and sure enough, the downward slope in it is statistically significant. Right? You can see that these things are sort of bouncing around. There's some randomness, so you want to use regression to like really confirm that that implied delta is increasing with the time delay to the delayed outcome. And sure enough, they satisfied themselves that the slope of this thing, right? This would be sort of like delta I equal to some intercept plus some slope turn times the delay cap t plus some error, and they confirmed that slope is positive and statistically significant. Now, just to make sure that you understand the role of beta, right? Because what's going on is that beta is affecting all these things, but in relative terms, it's affecting the short-term trade-offs more, right? Because, for example, to explain the trade-off between 250 versus some period in 10 years, right? The discount factor, D120 in the beta-delta model, is going to be equal to beta times delta to the 120th power, okay? So beta is doing a certain amount of the discounting here, but you think about delta, raised any number below 1 raised to the 120th power is going to be dang small, right? So in some sense, here, delta is doing most of the discounting, which means that a relatively high value of delta is going to get you a lot of discounting. Whereas in the trade-off between 250 and some value a month from now, right, the discount factor, D1, is just beta times delta.